In this lecture, we will discuss about the variable resistor in LTspice. This is an interesting topic to show you how to change the resistance over temperature or over time in transient analysis. In previous lectures, we have been using fixed resistance values in all simulations, such as in transient simulation or in AC analysis. Also, we know how to use step function to step over resistance and run multiple simulations. Now, we will have more discussion about variable resistors in LTspice. The credits go to William, Cesar, Santos, Ramajo, who brought up the request to add more detailed information about resistors, especially about variable resistance in time domain transient analysis. I found this tutorial very helpful and gives me some good insights about this topic. First, let's look at the resistance syntax in LTspice. You can press F1 to get LTspice help and search for resistors. So this is the syntax for resistor. The syntax is resistor name, that's the reference designator name, as R1 or R2, followed by node 1, node 2, and also a value. The resistor is across node 1 and node 2. The temperature coefficient Tc1 and Tc2 are optional in brackets, and also the temperature value is optional. The following function defines the temperature-dependent resistance. The nominal value is R0 times 1 plus dt. dt is the delta T. Delta T is the difference between the resistance operating temperature and the nominal temperature. The same resistance equation is rewritten in blue. In this lecture, we will discuss about temperature-dependent resistance and also time-varying resistance. Notice that the default temperature in LTspice is 27 degrees C, and also the nominal temperature Tnorm is 27 degrees C as well. The first subtopic is about temperature-dependent resistance. So this is a summary about temperature in LTspice, which has been shown in previous lectures. You can go to dot options to double-check the keyword temp and Tnorm. The default values for both are 27 degrees C. Temp is the default temperature for circuit elements instances that don't specify temperature, such as capacitors or resistors. If you want to change the operating temperature in LTspice, you can use temp as a syntax. You can go to this link for more information. The same information is repeated here. You can find it in LTspice help and search for dot options. You can see temp and Tnorm are defined as follows. The resistance has a temperature coefficient. The short name is TCR, stands for temperature coefficient of resistance. It tells you how much the value changes as its temperature changes. It is usually expressed in ppm per degree C. The TCR equation is defined here as R2 minus R1 over R1 times difference between T2 and T1. R1 is the resistance at room temperature. R2 is the resistance at operating temperature. T1 is the room temperature in degree C. T2 is the operating temperature in degree C. Here, let me give you an example. Assume we have a 1 kilo ohm resistor with TCR as 50 ppm per degree C. Notice that the ppm could be either positive or negative. That means the TCR can go up or down as the temperature rises. 50 ppm is equivalent to 50 out of a million. That means the resistance will not change more than 50 out of a million per ohm per degree C over the temperature range from minus 50 degrees C to 155 degrees C in this case. This is a real part from DigiKey. We can see the basic information as shown here. This is a surface mount 0603 package, 1 kilo ohm, 1% tolerance, 0.1 watt power rating, and plus minus 50 ppm per degree C. This is the information copied and pasted from DigiKey. Oftentimes, you want to double-check the specs by opening up the datasheet attached in this link. In this case, the datasheet gives the same ppm as plus minus 50 ppm per degree C. So now let's go to LTspice. This is the first example to show you the temperature-dependent resistance. So this is a simulation in DC operating point. So temperature-dependent resistance is very helpful to check the resistor on circuit level performance under different temperature. As shown here, we have 3 different resistors. Each resistor is powered by a current source at 1 milliamp. So this 1 milliamp is injecting into each resistor, and we are going to measure the terminal voltage as V1, V2, and V3 on the left-hand side of each resistor. This is an easy way to identify the resistance by just reading the terminal voltage. You can see here .temp 50 means in this circuitry, the operating temperature is defined as 50 degrees C, and we are using .op to run the operating point simulation. In this case, we just define the temperature coefficient Tc1 for each resistor. In the first resistor, we use plus 50 ppm. The second resistor, we use minus 50 ppm. In the third resistor, we use plus 50 ppm. In the third resistor, also the temperature is different from the simulation. It is defined specifically at 100 degrees C. That means the resistor R3 will have more resistance than other 2 resistors because it's working at a higher temperature. So nominal resistance is 1 kilo ohm for all cases. If you run the simulation, the result window will pop up and you can read the voltage over V1, V2, and V3. As we expected, V3 has the most voltage here. So this number, if you times 1000, they are representing the resistance over each resistor. And both resistance are deviating from the nominal value as 1 kilo ohm. If you close the result window and go to View and Spice error log, or simply press Ctrl with L, you can open the Spice error log. So this shows you some basic simulation variables, such as T-norm as 27 degrees C and the temperature as 50 degrees C as we define here. We just finished the temperature-dependent resistance. Now let's go to time-varying resistance. Just to recap what we have learned before, there are quite a few operations and keywords in LTspice. You can use them to build your own functions. Notice that the time is a variable in seconds in LTspice. We are going to use it later in an example. Also, LTspice supports a lot of mathematical functions as shown on this page. In the second example, we create a resistance that is changing with time as a sinusoidal function at 1 kHz. In this case, we put 1 amp DC from this current source into the resistor R1. The resistance is defined as a sinusoidal function as sine of 2 times pi times 1 kHz times time. Time here is the simulation time in seconds in the transient analysis. If we run the transient simulation and we look at the terminal voltage waveform as defined as V1, we can see that it is a sine waveform as we just defined. More interestingly, the voltage V1 can go to negative. This implies that the negative resistance is supported in LTspice. This is the third subtopic about resistance as a generic function of measured quantities. Although it may not be practical in real-world design, I just want to demonstrate what LTspice can do for you, just in case you need it. In this case, we change the resistance as the node voltage. First, we define a voltage called Vin. It is a 1 kHz sine waveform. The terminal voltage is defined as in. And similarly, we have the same circuitry as shown before. This is a 1 amp DC current source injecting into the R1. And we are going to measure the voltage over V1 to represent the resistance over R1. The resistance is defined as the value of voltage at the line name in. After we run the simulation, we check the voltage at terminal voltage at Vin and V1. We can see they are overlapping in time domain. That means the resistance is changing as the waveform of Vin. Also, this resistance goes either positive, 0, or negative as defined in sinusoidal waveform. That's basically everything for this lecture. Just to recap, in this lecture, we discuss about temperature-dependent resistance. I demonstrate how to change resistance over time in transient time domain simulation. And also, resistance can be a generic function of measured quantities. Please feel free to check the reference and explore more examples on your own. The LTspice source files are given in the course material. Please run each simulation by yourself. Here are the references for this lecture. Thank you. See you next time.